Hello, my name is Hannah Huff, and this is my Physics 2211 Lab 5 report. So getting into it, the purpose of this lab is to determine what force the two Beyblades strike each other with. The theory behind this will be covered more on the next slide, but the two big principles include angular velocity and collision types, specifically elastic collisions. Lastly, before we get too far into it, I want to establish the system as the two Beyblades with no other surroundings, or yeah, nothing else in the surroundings. There's the arena, but that's kind of excluded since it's a frictionless surface, so we're not worrying. So getting into it, we have the first thing we're looking at is the collision type. So the Beyblades end up striking each other very briefly and then moving apart, indicating an elastic collision where delta K equals 0. In addition to this, these Beyblades are made out of metal, so we can assume that the system will never change shape or mass. Next up is the angular momentum, which is r cross p, where r is the distance traveled between by the Beyblades until they hit, crossed with the momentum, which is calculated by multiplying m times v. Some assumptions we have are the masses of the Beyblades found on the internet and the initial velocities which were obtained using the tracker software. Another assumption made was that the surface that they were spinning on was flat and frictionless. So, giving you guys some context, here's the video of the Beyblades striking each other. As you can see, the ring flies off, but we're going to look at the very first collision from this video and use that to set our initial and final velocities. So this was done through a series of calculations. You can see the variables over here. And so the first thing that was done was collecting the variables. And yeah, next the principles for the conservation of energy were applied, first for the elastic collision, and then this also applied to the initial and finals, like equaling each other for the velocities as well as the momentums. Then moving on, we have the formula for like initial and final velocities. So linear momentum was found here, the kinetic energy was found here, and then step 2 is moving into the elastic collision correction, which gives the velocity after contact, which is the linear velocity plus r times the angular momentum. For this part, the tracker software was used. The axis was set to be parallel to the scaling lines, which were set in the first frame of this and are in dark blue. The origin was placed at the location of their first collision, which is the pink cross section, because it would be easier to calculate the initial and final velocities from that collision point, since they're like moving towards it, they hit and then they move away from it. So we're setting that as the center. Then yeah, here are the two graphs. That's the Beyblade on top. This is the Beyblade on bottom. Here's some cool looking graphs. Yeah, moving on. So the theoretical calculation showed a velocity of negative 1.84 and in the x direction and negative 0.61 meters per second in the y direction, which is equal to the final velocity if energy was conserved. Moving into the actual tracker data though, the initial velocity was negative 0.122, negative 0.104 meters per second for the top one, and then negative 0.245 and then 0.017 meters per second. And that actually ended up being different from the final velocities, as you can see right here, which means that the energy was not contained within the system and that it was not a purely elastic collision. So looking at a little what if there's a third Beyblade added into the system? It'd be pretty interesting. Energy theoretically should be contained, assuming it's purely elastic. However, we did see that the last one was not purely elastic and some energy was lost since the velocities did not quite match up. And also, this could be due to the angles that the Beyblades bounce off of each other. Anyways, that's all for my presentation. Thank you for watching.